I request all the participants to pay their attention to the session, and hopefully the session will be very much fruitful to you. So I would like to hand over the session to the ma'am.
Thank you for the warm welcome. So shall we begin the session?
Yes, ma'am. We are ready.
Okay.
Welcome. Sorry, I just joined a little late. Welcome, Janani, ma'am. Thank you.
Thank you.
Yeah, we are ready, ma'am. We can please start.
Okay. I'll share my screen and let's get started. So the PPT is visible, right?
Yes, ma'am. Please go ahead. Yeah.
Okay. At any point in case like the slides aren't moving as I'm talking and there's a mismatch between what I'm saying and what you're seeing, please let me know. This has happened multiple times, so I'm just saying this in advance. Let me know and we can kind of sort that out. Anyway, welcome everyone to today's session. Thank you for inviting me to this amazing effort to inculcate quantum into our learning and education platform across the country. So today's session is based on a topic from QT-04, and the topic is running quantum algorithms on cloud-based quantum processors. As I was introduced earlier on, my name is Janani. I'm a quantum engineer at IBM Quantum team in IBM Research Bangalore. I am part of the technical support team, and we call ourselves IBM Quantum Support. So that's just a very brief introduction to who I am and what I do. So let's get started with the session. So what are the objectives of this lecture? Whatever contents we will study as we go on, these are some of the main points that I wish to convey, and I hope everyone can follow along. So the first thing is, what does the quantum computing pipeline on cloud look like? So as you know, like if you want to run a program on a quantum computer, nobody is like going to a particular site and nobody's going to a specific place in order to access a computer. We all use the laptop right at our home or office or school, wherever we are, in order to submit some kind of a workload and then run our programs on a quantum computer. And this is obviously thanks to the advancements of whatever we have on cloud, and because we can run these quantum programs on cloud. So what does the quantum computing pipeline on cloud look like? So that is one of the first objectives of what I hope to convey in this lecture. Then what are the requisites for running quantum circuits on quantum processors? So there are specific frameworks and essential processing that you need to do in order to be able to run quantum programs on quantum computers. And this is all the more important because not every quantum computer is built the same. There are subtle differences across different quantum computers, which we will discuss as we go on. So what are the requisites for running specific quantum circuits on like specific kinds of quantum processors? This is something we will discuss. Then what are some of the nuances of quantum hardware? You need to understand this in order to be able to not just run your quantum programs, but also get meaningful results from them, or especially given that we are just slowly moving from the NISQ era to the utility era. So we are now able to get some useful results from quantum computers, and that is thanks to understanding what are the issues with the hardware as they are now, and like what we can do to kind of face off against these issues and tackle them using specific methods. So how to go from a quantum algorithm to implementing the quantum algorithm? This is also something we will see. Then how can we optimize the implementation of the workloads on the hardware, which was essentially my previous point of how can we tackle the issues that we see in the quantum hardware that exists today, because we have not yet reached fault tolerance where you can get extremely efficient and correct results from quantum computers, because quantum error correction is still not there. We have not found the perfect quantum error correction frameworks yet. We are still developing that. So before we can get there, how can we optimize the implementation of the workloads we have on hardware? Then we will also look at some advanced techniques which we can use for like the efficient implementation, as well as how can you post process your results, and the rest. So let us get started with this lecture. First of all, what does the anatomy of a quantum computing service look like? So as a user, you are just going to, say for example that you've come up with a quantum algorithm. Now, how do you go from here to implementing your quantum algorithm on a specific piece of quantum hardware? So the first step that you will have to do is to write your quantum algorithm using a quantum programming language. So, you can use an SDK. There are so many SDKs today. You can use a quantum SDK like Qiskit, Bracket, Pennylane. There are so many. You use one of these quantum SDKs and you write down a program using a quantum programming language. From there, you access some cloud service using another quantum SDK or some other service. In the case of IBM Quantum, the way to access the cloud service is through using Qiskit runtime. So you first come up with you write your quantum algorithm using a quantum programming language, and then you connect to the cloud service, which in the case of IBM would be Qiskit runtime service. So from there, whatever your job or workload is done, once you submit it in a specific way, that gets sent to a server in some laboratory. So then from the server in the laboratory, it's again sent to some control electronics. Now, this control electronics is one of the most important aspects of before it gets actually implemented, because these control electronics will convert your quantum program into pulse sequences. And these pulse sequences will then be sent to a quantum computer in order to be processed. So once the processing is done, and then you get your final state or whatever, once that processing is done, that information is again sent back to the control electronics. From there it is sent back to the server in the laboratory, and from there again it is sent to the cloud service, which is to the cloud service. And from here, Qiskit runtime service in this case would help you retrieve the results, or it will send the results back to you, and you interpret it again using Qiskit, if that's the quantum programming language you've used, and you get the results. And then the post processing is up to you. So very generally speaking, this is not only restricted to Qiskit. This is common if you want to use any kind of hardware, commercial hardware that is hosted on cloud. This is what the general pipeline looks like, whether it's going to be Amazon Bracket or like whether it's IBM's Qiskit. Using these programs, if you're running on quantum hardware, this is the general pipeline. I saw a question come up asking whether it's the same as simulation. No, this is the furthest from using a quantum simulator, because quantum simulator, you can have a quantum simulator on cloud, but then you're not okay. So if you have a simulator, whether it's, first of all, you can have a simulator on your laptop itself. There are many local simulators available across many quantum SDKs. So if you are using a simulator, local simulator, then everything will be restricted to just the first part. Everything will be contained by just the user. But say suppose you're using a simulator which is hosted on cloud. A quantum simulator is essentially a classical computer which mimics what a quantum computer can do, right? So it's not it's not hardware in the sense that these steps where you go to a server in laboratory, control electronics, and these pulse sequence conversion, none of these steps would happen. You will connect to, like as a user, you will connect to some kind of a cloud service, and from there it will be sent to the simulator. The simulator will run your program, give the results back. Because that's just a classical computer, you don't need to go through these steps, such as converting using control electronics to convert your program into pulse sequences or the like. So then it is sent to the simulator. The simulator will process your results and it will send it back to the cloud service, and then from there again you can retrieve the information back. So this is what a general framework of how you can run a program on a real quantum computer uh, used through cloud, right? So now what next? So, I mean, as I said, whatever you are doing, everything will be restricted to just this sphere, right? You are, as a user, you will talk to the cloud service, which in this case, in the case of Qiskit, would be Qiskit runtime if you want to use IBM hardware. So everything is going to be restricted to just this sphere. So what does the example of a final result that you can get back from the quantum hardware look like? it can look like something like this. This is the result from something we called as a sampler, where you have a quantum state and you are looking at the final distribution. You give a few number of shots, and as per the number of shots, you make that many measurements, and whatever state you observe finally, that you make a histogram plot, and this is what the plot can potentially look like. Now, if you use something, there is another type of primitive which is called as an estimator, which helps you calculate expectation values. What is an what does the estimator do? It calculates the expectation values based on an observable that you give. And that is calculated in some sense as an average over all the states that you're actually measuring. Now, I don't want to go too much into detail on this topic because I'm sure you will be discussing these things in further lectures. But okay, what does the count represent? So say, for example, that I want to prepare like say I have a specific circuit, and I want to build a specific say for example, I want to build a specific state, say for example a bell state. Okay, so how do I construct a bell state? I have to prepare the bell state using a quantum circuit. So when I prepare a quantum circuit, the final state that is contained will be in a superposition, but you cannot directly measure the superposition, because whenever we perform a measurement, the quantum state will collapse into a classical state, and you can only measure a particular out of say for example, if there are 8 possible states, so in this case you would have used a 3 qubit circuit. Okay, so in this case, this is again a GHZ state, which is a generalization of the Bell state on 3 qubits. So even if you prepare the superposition 000 and 111, the only thing that you will like when you measure, it's not guaranteed that you're going to, you will not be able to get this 000 and 111 through a measurement. You have to make multiple measurements, and as you see, this is 507 and this is 435, right? So this the fact that the probability amplitude of these two states is almost half indicates the fact that this is a 3 qubit GHZ state, and you observe these states with a very small probability. I will try to discuss this in a little bit more, it will make a bit more sense if I discuss this in further slides. So let's keep going, and I will revisit what these counts represent. Okay, so before that, let us discuss what is a quantum SDK, right? Here in this part, we learned that a quantum programming language is what helps the user kind of convert their quantum algorithm into a quantum program, which can be run on a quantum computer, right? Ultimately. So what is a quantum SDK? A quantum SDK is a software development kit, which is a collection of tools, libraries, and frameworks that enable developers to write, simulate, and execute quantum programs on quantum computers or quantum simulators. What does it typically include? It typically includes programming language or API. It contains some kind of a quantum circuit simulator, object. It has a way to, it gives you some kind of way to access the quantum hardware. It will contain compilation and optimization tools, which are extrememely important. And it would also potentially contain some visualization tools. So what are some common, very well-known SDKs? You have Qiskit from IBM, you have Penny from Xanadu, you have Circ from Google, you have Bracket SDK from Amazon. And there are also some not so common quantum programming frameworks, with, for example, OpenQASM. This is a quantum assembly language for intermediate representation. This is not something that you can, use the same way that you use these things. You can write a program that is completely, you can write your quantum algorithm if you come up purely in OpenQASM, but there is something extra you might like. You may have to take care of some more steps manually from your end, if you want to use something like OpenQASM for running on, say, for example, hardware. Then you have, SDKs, for example, called as Strawberry Fields. This is an SDK for photonic quantum computing. And you have Q# for Microsoft Quantum Development Kit. Now, let us briefly discuss what is Qiskit, right? Excuse me. Now, in particular, Qiskit, I'm discussing Qiskit because that's what we will be looking at in terms of the programs that we may see today. It will be based on Qiskit. So I'm going to briefly discuss what is Qiskit. Qiskit SDK is an open source SDK for working with quantum computers at the level of extended quantum circuits, operators, and primitives. So, for example, how is it different from OpenQASM? In OpenQASM, you would, have a way to represent your qubits. You would have a way to, implement specific gates on, specific qubits. But then, like, what if you want to do something a little bit more advanced, right? In that case, you will have to have a level of abstraction over something like OpenQASM, which is an intermediate representation language, right? So in these cases, languages like Qiskit or even Amazon Bracket or Cirq, Penny for different purposes, you can use different quantum SDKs. And in this case, as Qiskit is especially useful if you want to use it at the level of extended quantum circuits. Say if you want to build some sophisticated quantum circuit, right? It's not going to be easy to like write line by line, say you have 100 qubits. If you want to apply Hadamard on 100 qubits, it's easier to say write those 100 lines using specific syntax in Qiskit rather than say directly in OpenQASM, especially considering that if you want to build more sophisticated circuits, you might even find some template circuits in the Qiskit circuit library. So if you want to use that, if you want to use some operators or primitives, which we will come to, primitives is a okay, we'll come back to that. But these are some constructs which exist inside Qiskit SDK, and this helps you write your quantum algorithm in a more easy way. Then you have Qiskit runtime, which is the cloud-based service for executing quantum computations on IBM hardware. It is essentially helping you at this level, right? If you want to go from here and then send your program to the server in the laboratory, you will use Qiskit runtime service in your program. And once you get through this part, from here to here, Qiskit runtime will do a lot of things, a lot of talking back and forth in this part also, where you're sending and in the retrieving of the results as well. So that's where Qiskit runtime is going to be useful. Then what is Qiskit patterns? Qiskit patterns is a framework for breaking down domain-specific problems into stages. Say, for example, you have a quantum algorithm, right? Now, how would you, what did you develop your quantum algorithm for? Say, for example, it's an optimization algorithm, but you want to use this optimization algorithm to solve an optimization problem. Say it's a quadratic unconstrained binary optimization problem. Now, QBO problems are so common across various fields, right? So you can formulate various QBO problems to solve. A QBO problem is basically an optimization problem in some sense. So how would you adapt, your quantum algorithm, which is an optimization, algorithm, to solve some specific use case? So Qiskit patterns is a framework for breaking down your overall pipeline, right? How do you go from point A to point B, where you solve the actual problem using your quantum algorithm? You need to break it down into several steps in order to be able to do that. So this is a framework which we will discuss in upcoming slides, right? And finally, what is the Qiskit ecosystem? The Qiskit ecosystem is a collection of software and projects that build on or extend Qiskit. Say again, for example, that you've come up with a very new quantum algorithm and you're publishing a paper on that, right? Now um, you want to write this quantum algorithm in such a way, you want to package it up nicely such that anybody who wants to use it or like say experiment using that algorithm can do so. So you can do something, there is something called as a Qiskit add-on. You can package up your quantum algorithm in such a way that it's a Qiskit add-on, which would then become a part of the Qiskit ecosystem, and people would be able to access that Qiskit add-on and use your Qiskit, they can use your quantum optimization algorithm to do, to perform experiments on their own or to verify your results, so on and so forth. So what does the Qiskit ecosystem actually consist of? You have the Qiskit SDK, You have Qiskit IBM runtime. Qiskit SDK is the quantum programming language which we spoke about before. We have Qiskit IBM runtime, which is going to help you, talk to the cloud services and, eventually access your quantum hardware. You also have Qiskit Air, which is actually a package with which you can use several different kinds of simulators on your computer, right? You can use, if you want to implement your programs using a quantum simulator, you can use Qiskit Air. Then you have Qiskit serverless, which is again which is a framework to be able to implement your um, workloads in a much more efficient way. Say, for example, sometimes when you run a program, you have to babysit it, like make sure that it's running properly, that your kernel doesn't time out in your Jupyter notebook, etc. Right? But serverless is something that can take care of this and also make sure that there is no lag in certain parts of your program. Then you have something called as Qiskit functions. Qiskit functions is it can be more for say for example there are software leaning companies, or you want to develop some kind of a product which has to be run on quantum hardware, right? So you can come up with a Qiskit function which is going to be run on Qiskit on IBM quantum hardware, but you can make specific optimizations for your algorithm to run on that hardware by coming up with a Qiskit function. So that is again another thing. Then you have Qiskit add-ons as well, which are other packages, because since which are other packages that other people come with. For example, M3 is a really good Qiskit add-on because it helps you. It's basically an error mitigation, readout error mitigation related package. So you have M3, then you have Qiskit machine learning, you have Qiskit algorithms, etc. I think I saw a question, but it's not visible to me. So I'm just going to come back to this chart. I'm going to maximize this and check. Can someone tell me what is the question, because I cannot see it in the window right now? There was a question, something about changes in Qiskit. Or we can come back to that later. Hello, am I audible?
Yes, ma'am, you're audible.
What's the question? Like, can someone read it out for me?
As the Qiskit are changes every time, we face problems to run the algorithms.
Okay. Yeah. So, I mean, okay. In this case, that's why it's important to understand the framework of your algorithm, right? So, if for example, you're using Qiskit machine learning or Qiskit algorithms to run some like particular, say you're using these packages to run a particular algorithm. The issue is that, excuse me, I'm just getting a call. Yeah. So, yeah. Um, the reason there are, first of all, let me answer why there are frequent changes in Qiskit. If you look 2 years ago, you would not be able to run anything, say, for even 60 qubits. It would be very difficult for you to run a program. But now we are very easily able to run utility scale workloads, which are, which are quantum programs which can run for over 100 qubits. And this is not something that is that you can simulate classically very easily. It's very difficult to actually run like if you want to run a quantum program for beyond 50 qubits, it's going to be very difficult to do it even on a simulator, right? You can do it, it's not impossible, but it's very difficult. And as you go to 100 qubits or even beyond 100 qubits, you say you want to go to 200 qubits, 400 qubits, it becomes much 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 harder and harder. So as now we are, again, as I said, now we are at a place where you can run utility scale workloads. So if you are able to run utility scale workloads, you need to bring changes to the software stack so that it can keep up with the advancements in the hardware, right? So because of that, there will be changes, especially now, since like it's in a very rapid development phase. But it's not impossible to kind of instead of using these packages, if you know how to write the algorithm natively in Qiskit, there are many ways to actually translate the program such that it can run on a more recent version. So I think that, like, I mean, of course, these packages are there, and if you downgrade the versions, you might be able to use. But then if you want to run the program on a real hardware, right? See, these things will still run on a simulator. But if you want to run it on real hardware, you have to be able to use like the more recent versions of Qiskit. And those are optimized such that they can be more compatible with the new and developed hardware. So when it comes to that, you make these optimizations, not only will you be able to use more qubits and solve bigger problems than you used to, but you will also be able to get meaningful results using techniques such as error mitigation, which I will come to like towards the end. There are so many techniques which have been developed now, and that is actually possible because we made changes in the Qiskit SDK. So if it was as it is, you will not be able. 2 years ago, you would not have been able to run utility scale workloads on your like computer, but now you can, and they can run within 2 hours. So these are 100 qubit plus workloads which we're talking about. So in that sense, yeah, they will change. But if you learn how the algorithm is built like by itself rather than just using a function which is written in a package, you can very easily like write it in the more latest version of Qiskit. And honestly speaking, very you will see that a lot of functionality which was there on the add-on packages are kind of built into Qiskit in the newer and newer versions. So in the initial phases, you will kind of see a focus to build the basic structures such as the primitives and like the backend related structures. So if you see what was the newest thing with Qiskit 1.0 which came out last year, we had a backend v2 object which was formed. Then we had primitives v2, which is like the sampler v2 and estimator v2. And then we had a lot of error mitigation which was added to Qiskit IBM runtime. And like the main optimizations that were done were so that they can support parametric workloads which come in the form of variational quantum algorithms very often. So these things have been made much easier in the newer versions. So and you could not have done that without like making some compromises. But the same workloads that you used to run earlier on, you can run it if you, again, as I said, write it in the more recent version, right? And it will definitely work better as well in most cases. So I hope to some extent that answered the question. Okay, I'm seeing many questions that have come up. Okay, I'll try to cover them, but let's go. Maybe some of them will be answered as we go on with the lecture. So anyway, so getting set up with Qiskit. So like first of all, if you want to use the Qiskit runtime service or through the open plan or whatever, you first need to set up your have a setup in order to be able to access the IBM hardware. And you have to set up your you have to create an account and set up your credentials through like say an IBM quantum platform or IBM cloud. So I will quickly show the website. Okay, it got closed because so I'm just going to stop sharing very briefly, just a second, so that I can open the okay. So now I'm going to share the screen again. I hope this screen is visible. So if you can see, this is like the IBM Quantum Platform account, the classic sorry, this is the classic IBM Quantum Platform account. You can see, so this is called as an instance, and this is very important. So this is what you would usually see. So this is the open instance, and this is your API token. So please take note of these things. We will like as we go on, we will see more details. And if you create your account through cloud, so this is what the new IBM Quantum platform, which is hosted on cloud, looks like. So yeah, here the instances are visible in this side, and you can create an API key in this side, and you can switch between different instances from here, right? So now coming back to Coming back to the presentation, so you have to set up an account in one of these places, and you can find more information here. And you have to install certain packages, but we will come back to that later. So let's not talk about everything before we get to the topic, right? So next we will discuss Qiskit patterns. So now what is a Qiskit pattern? So say, as I mentioned, say for example, you have a problem and you have come up with a quantum algorithm. Now you want to solve this problem using the quantum algorithm that you've come up with. How can you do that? So the very first step you need to go through to do that is to be able to map your problem to a quantum circuit, and you need to map your problem to quantum circuits and operators. What does this mean? Say for example that I have like I have I know I have I know VQE, or I know QAOA, and there is a particular protein structure, right? I want to predict the structure of this protein using so I know how to formulate a protein structure prediction problem as an optimization problem. Now I want to be able to solve the protein structure prediction problem using, say, for example, VQE. Now, what would I do? I will have to encode the structural parameters of the protein into my qubits, and I'll have to prepare a quantum circuit or a state, and like using, like say for example, because I want to solve it with PQE, I will come up with an ansatz, and I will encode these structural parameters of the protein into the quantum state that I'm the parameterized using the parameterized quantum circuit. I will create a general state which contains the variables related to these geometric parameters of the of the protein. So then when I optimize it based on a given specific cost function, say for example, for the case of a protein, the best or the final structure would be the minimum energy of would be the structure corresponding to the minimum energy of the protein. So I will come up with an expression to find the energy, which can be done by calculating the expectation value using an estimator. And then I would have to optimize that in order to find the structural parameters, which would be encoded by, say, some thetas. So then I will have to post process the results. So I have kind of skipped the steps here, but then the first step, as I mentioned, would be to map the problem to quantum circuits and operators. What would be the quantum circuit here? Because I'm using a VQE, I will use a specific ansatz, like say a hardware efficient ansatz or some kind of an ansatz as the quantum circuit, and I will encode the structural parameters of that protein into the qubits, right? So whatever state I'm preparing is having aspects of the problem encoded in the quantum state prepared, because the quantum circuit prepares the quantum state. Then the operators, in terms of the operators, that would be the energy aspect of that particular protein, right? Because I want to minimize the energy that I'll get the cost function, or I can construct the cost function for VQE by doing some expectation estimation. I will encode the energy related components or the cost function related components by using operators, which will come operators. We say operators here, but in some sense it's an observable, right? Then optimize circuits for target. So the second step of Qiskit patterns would be to optimize your circuits. Once it is ready, you have a quantum circuit, you know what operators you want to use. Before running it on the hardware, you have to optimize the circuits for running on some specific target hardware. Then you execute this on the hardware, then you get the results back, and then you post process the results in order to, so in this particular case, your final step would be to retrieve the thetas and construct the final structure of the protein back using those thetas, right? So in general, for any problem, this Qiskit pattern is a framework that allows you to generalize how to go from specific how to take a specific problem, an appropriate quantum algorithm to solve that specific problem, run it on quantum hardware, and get some meaningful result out of this, out of running something on a quantum hardware. So what do we need to do to map the problem, right? So we have to start with a numerical representation or a mathematical model, right? In the case of the protein, case of protein structure prediction, if you use, say, the lattice formulation, you will basically consider a template lattice for the protein structure, and using the template lattice, you will kind of say that the first protein can have four possible, it can have four. If you just use a very generic non-optimized encoding, you can say that the say it's a 10 a protein with 10 beads. Then in a lattice, say for example a square tetrahedral lattice, you would have four possible uh, positions for each bead, right? So you would say that the first four qubits represent 1 2 3 4 of the positions of the tetrahedral lattice, first site of the tetrahedral lattice. The second one can have again 1 2 3 4. Now as you go on, you will have to kind of reduce the redundancies and make the encoding more efficient, but that's a very very basic way of doing it. Now once you have all these qubits, once you've encoded all the structural parameters into the qubits, that is the starting numerical representation, right? Or the lattice is the starting numerical representation, which you can then map to a quantum computing representation, which is in this case, you're mapping the various sites of the lattice into the qubits. So that is your map to quantum computing representation. Now, once you have done this, you have to choose a quantum algorithm, because the circuit you're constructing from there will depend on what quantum algorithm you've chosen. Say if you use a VQE, then you will use a VQE circuit to prepare a quantum state. If you choose to use a QAOA, you will come up with a QAOA based quantum circuit to prepare the quantum state. All right. So that's the very first step, right? So before we go there, what is this? This is the coupling map. This is something that we call as a coupling map for a particular hardware. In this case, this is a hardware with how many? This is for a hardware with 127 qubits. As you see, the maximum, we start from 0. The maximum is 126 qubits. So this is an eagle. This is basically an eagle backend. We will get to what that is in the upcoming slides. So the very first step of the Qiskit pattern, map problem to quantum circuits and operators. This is where you start, right? Now, this is what you do for the case of a protein structure prediction problem. So what if you had a graph problem instead? What do I mean by graph problem? Say I have given you a graph, uh, and I say that I want to solve the max cut problem. If we have time, that is the problem that we will see today. But yeah, there are various graph problems that you can come up with, right? Graph coloring problem, max cut. There are so many different. What is the shortest path that you can take on a directed graph? There are various problems. So in those cases, you can encode the nodes of the graph as the into the qubits. So yeah, these are some of your options. Uh, just excuse me for a second. I think I need to take this call. I'm very sorry. Sorry about that. Am I audible?
Yes, ma'am.
Yeah, okay. So let's proceed. So let us proceed. So now that we have we have a way to map a problem, how can you build a basic circuit, right? So to build a circuit with a Qiskit SDK, like say this is a very basic Bell state circuit. So the foundation of creating a quantum program is a quantum circuit. So like gates, measurements, resets, and any way to prepare a quantum state, you specific target quantum state you have in mind, you have to manipulate the qubits, right? And to manipulate the qubits on a gate based quantum computer, the way you would do it is by implementing gates. So this is just a very basic Bell state circuit. You have a Hadamard on Q0, you have a C naught acting on 0 as with 0 as the control and 1 as the target. Then this is something called as a barrier. Then you have the measurement on, say, the 0th qubit and the first qubit, which is being stored in these like classical register, which is of the name MEAS, standing for measure, right? So yeah. So to build a quantum circuit with as Qiskit, to start with, you have to initialize a register with qubits. Then you add, qubits to you add the qubits to a circuit, and you perform operations on those qubits. So you can see this is just a very basic Bell state circuit program. Now, Qiskit SDK includes a library of standard gates and circuits. You have a way to call the Hadamard, Poly, C naught, and there's a circuit for quantum Fourier transform as well. And you can also call variational ansatze from parameterized quantum circuits. You can also call for some specific variational ansatze for chemistry or combinatorial optimization. You have hardware efficient ansatz, etc. Now, the second step would be to optimize your circuits for target hardware. Now, before we go into more detail on this topic, we have to first understand, a little bit more about the nature of quantum hardware. So, what is a required step? So, there is a definitely required step whenever you want to optimize your program for running on hardware. And this extremely important step is called as transpilation. Transpilation basically stands for translate plus compile in some sense. And what this represents is to basically take an abstract circuit you have, or a virtual circuit is a better word, and convert it into a circuit that can actually run on a target hardware. Now, let's go back to this figure, right, which we saw, what I mentioned as a coupling map. So this coupling map is it's a picture that shows you the connections between various qubits on a specific quantum computer, right? So this is a 127 qubit quantum computer, and if you see, you have 0 connected to 1 and 14, you have 1 connected to 2, you have 2 connected to 3, and so on. And say I come up with a circuit where I'm implementing C naughts between 0 and 1, 0 and 2, 0 and 3, 0 and 4, and so on, right? Now, if you see in this particular diagram, you can see that 0 is adjacent to 1 and there is a connection between these two. But there is no connection between 0 and 2, or 0 and 3, and 0 and 4, and so on. So in this case, how will you actually implement a C naught gate, right? When you write your quantum program, you can implement a C naught between these qubits. But how does it actually run when you implement on a machine? Because these qubits aren't directly connected, right? So, and another thing is, we will come to this when I will again come back to this point. But in a gate based quantum computer, when you construct a quantum computer, you cannot possibly create it with every single imaginable gate, right? You only come up with a minimum set of gates, which you come up with a minimum set of gates which will then be useful in order to build any gate that you want. So what I mean by this is, you don't say, for example, that you want to build a circuit with rx, ry, rz, rxx, ryy, rzz, and so on, right? Now, when you build a computer, you don't want to directly make your machine implement all these gates in by itself. So when you build a quantum computer, it will only be able to when we build a quantum computer, we give something called as a basis gate set for that particular quantum computer, which consists of a minimum set of quantum gates with which you can construct any gate that you want. So essentially, when you give a virtual circuit for the quantum computer to run, and you do this transpilation process, one of the steps that would happen is to translate the So one thing it would do, as I mentioned here, is even if you cannot implement a C0 directly between 0 and 2, it will do some, it will do a specific thing in order to let you implement a C0 between 0 and 2. And if you cannot say implement a C0 directly into on your quantum computer, because it's not a part of the basis gate set, it will decompose your C0 into various other operations so that you are able to implement the C0 gate. So another optional step is to verify your circuit with simulation. As I mentioned some time back, at the best you can do on a quantum simulator is to go up to 50 qubits, right? Like if you want to run like really, first of all, just thinking about it from a more sensible point of view, a quantum computer is a very expensive resource, right? You want to be able to use a quantum computer to solve problems which are suitable to be solved on a quantum computer. Just practically thinking about it, if you want to calculate 3 into 5, you're not going to sit and write a sophisticated Python program to do that. At most, what you will do is pull out a calculator to calculate 3 into 5, right? So um, you need to use resources proportional to the complexity of the problem you want to solve. So in that sense, like if you want to run so you cannot use a simulator to solve all kinds of problems. You can use it for maybe some smaller problems, but as you move on to bigger problems and you want to implement on hardware, you also want to make sure that your program is optimized to run on a hardware. So you first verify your circuit with a quantum by running it, say for example, on a smaller scale on a quantum simulator, and then as you scale up, you then implement it on quantum hardware. So real quantum devices are subject to constraints. As I mentioned, you have something called as a basis gate set. So only a limited set of gates can be executed directly on the hardware. Other gates must be rewritten in terms of these basis gates. So if you look at, for example, say even a C0 gate, you cannot directly implement a C0 gate on either say, I will come to that, but then I'll come back to this point later. You also have to consider qubit connectivity. Only certain pairs of qubits can be directly, can directly interact with each other. And aside from this, you also have, each operation also has some chance of error. So circuit optimizations can also affect performance. So you also have to take care of the fact that you are by saying that I'm going to optimize my circuit by doing various things, you keep adding more and more gates. These gates themselves will have some noise associated with them, right? So that shouldn't pass over a threshold and cause your overall computation to be very bad. So okay, this is a very, this is you can classify, you as such for anything, any topic, you can come up with various types of classifications. Just to talk about quantum computers, like in one way you can think of, one way you can think of classifying quantum computers would be based on the mode of computation or the way the system evolves in your quantum computer, right? So a gate-based quantum computer would be one which is, again, it's going to be, there are various traits, but just to generally say, you would evolve systems by putting gates from a specific basis gate set. So for in photonic quantum computers, you manipulate your qubits using light, because that's how your qubit representation itself comes from kind of a laser. So the way you manipulate that would also be the way you manipulate lasers, for example. Then you have quantum annealers, which are again a separate type of the quantum system there evolves through the process of annealing. And then you have topological quantum computers, which are, by the way, still in pretty much the developmental stage, right? So to come back to IBM quantum computers, the two most recent, the two most recent generations of quantum processors that mark significant advancements on the company's quantum computing roadmap. These are Eagle. Basically, Eagle is the name of the chip, quantum chip, and Heron. So what are these and what's the difference between the two? So IBM Eagle processors, basically they have a qubit count of 127 qubits. In terms of architecture, they have introduced advanced 3D packaging techniques allowing signals to pass through multiple chip layers. This design also supports high density input and output without compromising on performance. In terms of performance, it has achieved a quantum volume of 128, indicating that it can, handle some complex computations. What is the significance of this? When it was unveiled in 2021, Eagle was IBM's first processor to surpass the 100 qubit milestone, and it's nearly double the count of the predecessor, which was the Hummingbird processor with 65 qubits. For Heron, let me first actually talk about the significance, because it was introduced in December 2023, and it's a new class of high performing, IBM quantum processor, and it serves as the foundation for IBM quantum system 2. Essentially, as we are scaling up on the number of qubits we want to have in a machine, what was discovered was that if you put all the qubits in a single chip, it no longer keeps performing well. Like as you put more and more and more chips in this, more and more qubits in the same chip, it wasn't doing very well in terms of performance and fidelity of the quantum compute that was coming out of it. So what was decided was that we build individual chips with slightly smaller number of qubits, and we link multiple of these chips in order to build a bigger chip. So the Heron processor was the very first innovation that came along those lines, and it's really amazing in the fact that it features fixed frequency qubits with tunable couplers. Now these tunable couplers are like the main good feature that came out of it, because it virtually eliminates all crosstalk errors and enhances overall performance. Again, as I mentioned, it has a modular design that facilitates scalability and integration into larger systems. So you can use multiple of these chips to build a bigger chip. And it also demonstrated a 3 to 5 time improvement in terms of device performance over the Eagle processors, and attributed to reduced error rates and enhanced gate fidelities. Now, some of the latest features on Heron processors that are available are like error mitigation. I mean, some of these are also available in Eagle, but you have, like they are coming through, say, the Qiskit SDK or Qiskit Runtime SDK, but these are like, these features are being supported on Heron processors, especially if you look at the features like fractional gates. These are for the newer Heron processors, fractional gates, and the new dynamic circuits that's actually coming up very soon. So you have error mitigation techniques like ZNE, PEA, and various others. You have error suppression in terms of dynamical decoupling. You have dynamic circuit features, which is basically conditional measurements and resets, if else, switch else, blocks, etc. And you have fractional gates, which are offering better support for running variational algorithms. And you have Gen 3 Turbo, which helps with faster execution and a clocks of almost 200K, right? Now, the challenge of running an abstract device on a specific quantum device, the solution to that is transpilation, right? So if I have a Hadamard and two C-naughts on a particular set of qubits, before actually running it on a quantum computer, I have to do this process called as transpilation. So when you actually transpile the circuit, this is what it looks like. So this is transpiled on an Eagle some Eagle backend, because the Eagle basis set consists of ECR gates. ECR gates are 2 qubit gates. So if you had done the same transpilation on a Heron processor, you would instead see some CZ gates, because the 2 qubit gate on the Heron processor's basis gate set is a CZ gate. So depending on which hardware you're actually implementing in, this transpiled circuit will also look completely different, right? So the syntax for doing this transpilation is also changed a little bit. Initially, you could just say transpile of QC and you would be able to transpile the circuit. But now we use something called as a pass manager. So the transpile function was doing that initially, but now we are using the pass manager because this is the specific, what to say, this kind of this way of doing it makes it more efficient down the line. So you basically initiate a pass manager, which and you can use this generate preset pass manager, which kind of like helps you come up with some good default options to do the transpilation. And you set this thing called as the optimization level and the backend. So because you have to transpile with respect to a specific backend, you have to mention the backend as well, backend as well in this particular thing. And the optimization level, basically in this case, pass manager, a pass basically, okay, like taking a step back, when you even after you get this right, before, like when you have to share, you have to make each of these gates happen one by one, get implemented one by one on the hardware. So a way to visualize how we can do that is by creating something called as the directed acyclic graph representation of this circuit, which is in short it is called as a DAG. So once you get the DAG, you want to you would manipulate the DAG, right? So pass manager, here we are, this generate preset pass manager, basically it comes up with a default set of passes which manipulate this DAG in specific ways at various stages, right? So when you go for optimization level 0 or 1 or 2, you have different set of passes which are initiated. At optimization level 3, you have a different set of passes, and this is supposed to be the most this is going to help optimize your circuit the most as compared to 2 or 1 or 0. But then it can also vary a little bit depending on the uh, depending on the kind of depending on the depending on the circuit you have. So what are the transpiler stages? You have initialization, you have layout, you have routing, you have translation, optimization, and scheduling. So in the initialization stage, your circuit is basically prepared for transpilation. So the very first step would be to decompose all multi-qubit gates into single and 2-qubit gates, because your basis gate set in the backend has at most 2 qubits. So if you have any gates which are say 3-qubit gates, say a control X, that would act on 3 qubits, you will decompose this control X into 2 qubits and single qubit gates, and then you would implement it. So in the very first stage, that is what happens, very simply speaking. In the second step, the abstract qubits of the circuit are mapped to physical qubits on the device. What does that mean? Let's go back to this coupling map picture. So when you say Q0 of, you say, for example, in this circuit, right, you're saying Q0, you say H of Q0, CX of Q0, Q1, and then you put a measure all. So you have 2 qubits here, Q0 and Q1. But when you are implementing Q0 and Q1, you don't necessarily have to, choose these exact same 0 and 1 when you're running the program. You can also use 32, 31, 32. You can use 123, 124. You can use any of these combinations. And in some sense, there are inbuilt mechanisms so that you choose qubits which have lesser noise. So if you look, 20 and 21 are slightly noisy qubits. That's why the colors are slightly different. So when you transpile, there are also ways to make sure that you are mapping these specific Q0 and Q1 to good qubits. And you can also make the choice and pick whatever you think is appropriate for your problem. So yeah, that's one thing. So yeah, that's the layout stage. So the layout and routing stage, so that's the layout stage, right? So now again, what does routing stage do? Say for example that I'm yeah, let's come back to this picture, right? say for example, I have a in my abstract circuit here, I have like a third qubit, I have a second and third qubit where I'm applying a C naught between Q0 and Q2 and Q0 and Q3 as well. So now if you look in this map, I can say for example, I can map Q2 to 14 because Q0 and Q1 already have a connection. I can map 0 and 1 here. I can map 2 here because it seems like there's a possibility that I can put a C naught here. Again, there's a small catch here because 2 qubit gates are also often directional in the sense that if you may be able to put a 2 qubit gate between 0 and 1, but not necessarily between 1 and 0. So there are cases like this as well. So if the 2 qubits don't have a physical connection, how would I implement a C naught? So a simple way I can do that is to actually put a swap gate between 1 and 2. So I will first put a C naught on 0, 1. Then I will put a swap gate between 1 and 2. And then 0 and 2 will be sort of adjacent, right? Then I will put a C naught on 0 and 2. And I will say, and then I can send the qubit, I can send it back, right? So there's a specific way to do that. But the way it's done is by inserting swap gates. So in the routing stage, swap gates are inserted to enable interactions between qubits that are not physically connected. Then you have translation, where the gates of the circuit are translated to the basis gate set of the device. So now if you have CNOTs, the CNOTs will get converted into, say for example, ECR gates and other gates in the case of an Eagle backend, or it will be converted to CZ gates in the case of a Heron backend. Then you have optimization, where the circuit is rewritten to minimize the circuit depth, which means that if you have a lot of redundant operations, those operations will sort of be kind of collected together and made more efficient by a single unitary being applied, for example. And then you have scheduling, where you cannot. So one important thing in quantum computing is that you cannot simultaneously put operations on, if you have a C naught between Q0 and Q1, or you shouldn't put two different operations on, 2 qubits which are interacting at the same time in some sense. If you do that, like, you will make a mess of your quantum state, and you don't want to do that. So to make sure that you're applying the operations one by one, you have to put some delay operations on other qubits while specific qubits are undergoing evolution. And in some sense, the timing of the circuit is taken care of by this scheduling step, where you add some delay instructions to align the circuit with the hardware timing. So you have some additional transpilation tools as well. You have the Qiskit transpilation service. You have you can write your own transpiler plugins, and you can you can do some tricks with the circuit knitting toolbox as well. Then optionally, you can verify your circuit with simulation. I'm going to skip this part because I think most of it, like some part of it, has been covered already by yesterday, some part has been previously covered in other lectures. So, but essentially it kind of helps to check if your circuit is ready for implementing on hardware. You have like a lot of simulation tools in Qiskit. You have a separate package called Qiskit Air, but you have some functionalities in Qiskit SDK also, mainly in the form of some fake backends, which basically mimic the bigger backend. They basically mimic the noise model of your original backend. So if you want to try like looking at what your results look like on fake backends, you can sort of test that by you can kind of test that. Moving on. Now you want to execute on target hardware, right? So to execute on target hardware, you have to understand something called as primitives. So what are primitives? They encapsulate the output of a quantum circuit. And in Qiskit, we have two main primitives. One is the sampler primitive, which gives you the counts. So now I know there was a question previously on counts, so I will come to that here. And you have the estimator primitive, okay, what is a sampler primitive? The output is a mapping of bit string to counts. So each qubit, as you measure how many times is it like giving a particular state, that is what you see from a sampler primitive. Essentially, this is done over depending on the state you're preparing. This will help you kind of reconstruct what is the quantum state that you actually prepared. So as I mentioned before, if you this is the Bell state circuit, right? So we start with 0 here and 0 here in Q1 as well. And as we put the Hadamard, Q0 is going to go into a uniform superposition of 1 by root 2 times 0 plus 1. Now, when you put a C naught between this Q0 and Q1, which is still at state 0, you will be preparing the state 0, 0 plus 1, 1, which is the Bell state, right? Now, this is superposition, right? How would you measure this superposition? You cannot, when you do a measurement, the quantum state collapses to a classical state. So you cannot measure 0, 0 plus 1, 1 directly. However, based on the counts you see, you can reconstruct your results and infer that your final state is a superposition. How would you do that? When you actually measure this state, say, and what are shorts? Shorts is the number of times you want to kind of do this experiment and prepare this state and perform the measurement. Each time, so for example, if I do this for 20 times, I am very likely to observe, because I have 0, 0 plus 1, 1. I'm very likely to observe around 10 times I might measure the state 0, 0, and around 9 times I might measure the state 1, 1, because in a real quantum computer, like, it's not likely that you'll get the exact result. You will find 0, 1, say 1 time, right? Now, if you look at the probability ratio, like you can see that, you've measured the 0, 0 state 10 times and 1, 1 state 9 times. So you can infer that the superposition here is going to be 1 by root 2 times 0, 0 plus 1, 1. Now 20 is a very low number, but ideally you would, at least depending on the number of qubits you're using, you want to like do something, a number which is significantly, say, close to 2 to the power n, because that's the number of states you would have in a basis. So if you have n qubits, you would have 2 to the power n basis states. So yeah, that is, I hope that kind of made some sense as to what counts represents. Now then, what is the estimator primitive? The output is the expectation value of an observable. So that is, it's so essentially you kind of get, in some sense, the average over all states of a particular physical quantity. Okay, so in quantum mechanics, you cannot directly measure certain physical quantities of the system, but you can infer what those quantities are by acting your quantum state like on an observable and taking the expectation value of that observable. So that is what helps you understand some physical quantities related to the system. So okay, is the estimator devoid of measurement? I mean, yeah, when you're using the estimator, you're not doing specific measurements. Yes. And the reason it is useful in many cases is because when you go for larger and larger systems, right? Say if I want to go for a 100 qubit system, then the number of basis states in that system would be 2 to the power 100, which is a huge number of states, right? So now if I want to sample over those many number of states, it's basically very kind of, it's not very efficient to do so, right? Like you don't want to like do your experiment for so many shots. It's pretty expensive. So in those cases, if you instead go for an estimation based approach in your algorithm using the estimator primitive, you don't perform these measurements exactly, but rather you still get the averaged outcome like to an acceptable degree. But I mean, like, irrespective of whether you're using a sampler or an estimator, say even using a sampler, you can make estimation calculations, and using some estimation calculation, you cannot exactly sort of come back to understanding exactly what would be the probability amplitude, but there is a way to kind of uh, like if you do sampling, find how to find the expectation value. That's kind of possible. But The point of using an estimator is so that we don't have to perform these extensive measurements in certain cases. It's a bit more efficient, right? So yes, in some sense, circuit would not, so when you construct the circuit, you don't put measurements when you build a circuit. When you build a sampler, you have to put some measurements. Otherwise, you won't be able to kind of get the counts properly, right? So that's just the way you construct these circuits. So now perhaps one of the most important steps, how to run a circuit on quantum hardware, you have to connect to the Qiskit runtime service. And to connect to the Qiskit runtime service here, this is an easy way to load a saved account. But ideally, let's go here very quickly because I don't know if we will have time to do the whole, we will have time for the demonstration. But essentially, to connect to the Qiskit runtime service, you have to write something like this. You have to, and let's look at the website as well. So when you come to the website, so this is quantum.ibm.com, right? So this is the IBM quantum platform through the quantum channel. So here you would write channel and you would write IBM_quantum. So the same thing, if you're connecting from quantum.cloud.ibm.com, you would instead use IBM_cloud as your channel. Then your in the instance, you have to insert your instance, which on IBM Quantum platform you can find here. So this is IBM Q Open Main. This is what most of you would see if you're accessing it from the open plan. So you insert your instance here. Then here you can copy your token and insert your token. If you write overwrite equal to true, if there is a saved account or if you are using like say an old API key, that would get overwritten here. And then you write set as default equal to true. So then if you use service equal to Qiskit runtime service, every time it will load this particular account. So then you can also give a name for your particular account. If you are someone who has like multiple sort of ways of connecting to the Qiskit runtime service, say if you have a cloud account and you have a account from the quantum channel, you can set specific names. And when you load the service, you can just say service equal to Qiskit runtime service, or you can, if you use double brackets, it will just load the default one which you have put. If you write name equal to and you give IQP cloud or IQP classic something, it will load that particular account. So the rest is just a way to, like this is just the general pipeline of running a basic circuit on on using Qiskit and Qiskit runtime on hardware. So what are the main steps? Okay. What are the main steps? You basically connect to the Qiskit runtime service. You connect to like a backend, then you have to define a backend object, which here in this case, you're choosing the one which is least busy, which means you're looking at the you're looking at the particular computer which has the least operations sort of going on, or sorry, least number of jobs queued on it, right? You can also specify something like a minimum number of qubits it should have. You can say 127 for the case of, in this case, it would choose some of the eagle or the heron machines. If you say minimum qubits equal to 156, it will choose only a heron machine. Then you say number of qubits. Then you can just initialize a small basic circuit. For running on sampler, you will have to use a measure all. So here we are using a sampler. So before like actually implementing it, you have to transpile the circuit. Now I didn't mention this, but what does the output circuit coming from transpilation look like? So that is something we call as an ISA circuit, which stands for instruction set architectures. ISA basically means instruction set architecture circuit. What that means is whatever is in the basis of your particular backend, the circuit that you are getting out of transpilation will only contain those particular gates. It won't contain gates outside of that instruction set architecture, instruction set architecture of your particular backend. So then you initialize a primitive. So here in this case, it's sampler. And the reason there is backend written in brackets, we'll come to that towards the end. But essentially, you invoke the primitive with your ISA circuit. So here in this case, if you give a normal circuit, there is a high likelihood that it may not run, because unless you write your circuit in the basis set of the specific backend, it might have gate operations which are incompatible with your backend, and it definitely will not be optimized to run on the backend either. So you always need to, if you are running on backend, if you're running on real quantum computer, transpilation is a no negotiation process. You have to transpile your circuit. However, that necessity is not so hard and fast if you're running it on a simulator. You can try this if you have never tried it before, but if you run like circuits on a simulator, whether you transpile it or not, it will still run. It may not run very efficiently, or like it may take a bit longer in certain cases than others, but it will still run. Not on all simulators, like fake backends, maybe it won't run, but it will certainly run on, say, Qiskit Air, like simulators, it can run. So yeah, now coming back to this, the input to the input to the estimator and the sampler can look a little bit different. So here we have an ISA circuit, but the input to the primitive itself is something that we called as a pub, or a PUB, which stands for primitive unified block. The pub for a sampler and a estimator look a little bit different, because for an estimator, in the pub you have to specify an observable, and you have to apply the layout of your circuit onto the observable as well. What does this mean? So an observable is going to be an operator on, say, a specific it's going to have terms. It's going to have operators, like, I mean, it's going to, for example, it can look like z z z z z for all overall n qubits. It can be a z z z on just 4 qubits, but then on which 4 qubits is that ZZZ acting, right? That you might already know if, for example, you're defining the observable as something like Z2, Z3, Z4, Z5, you know that Z corresponds to 2, 3, 4, 5, but how does the program know about it? So the way you have to do that is by applying the layout of the circuit onto the observable. So like if you do it appropriately, okay, even before that, uh, even if you have Z2, Z3, Z4, Z5, you still have to um, define your observable as I, Z, 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 and then the rest will be I's, because the number of terms in this observable should match the number of qubits you're defining. Otherwise, there'd be an issue. And furthermore, the reason we are applying a layout is because in the layout step of the transpilation, your first 0th qubit might have gone to, like, say, the 6th qubit. First qubit might have gone to the 7th, might have been mapped the 7th qubit, and so on. So that mapping should also kind of be the mapping information should also be in the observable. So to account for that, you will apply the layout on the observable as well. So the advantage of using, like the recent version of estimator, which is estimator v2, is that you can construct this pub more efficiently. So when you say ISA circuit and ISA observable, you can split this observable into multiple more observables, or you can run multiple different circuits with the same observable as well by specifying different PUBs in the same estimator run. So this way, it reduces a lot of work for you, because in the older versions, you had to manually create more circuits in order to run these workloads. So you can customize the Qiskit runtime behavior by controlling the shots, which is the number of measurements. More shots reduce statistical error but increase runtime. So there is a, I wouldn't say a very subtle trade-off between sampler and using a sampler versus an estimator, but in certain cases it might be more useful to use an estimator than the sampler, because if you want to measure over the entire basis to calculate a particular value, it's just not worth it, because not every state you're measuring might be covered in the number of shots that you're choosing, right? So yeah, so you can control the Qiskit runtime behavior with shots. Then you have error suppression, which is through dynamical decoupling. So at this juncture, I would just take a moment to kind of mention that there is a difference between different terms, right? Error correction, error suppression, and error mitigation are all not the same. They're all subtly different. So maybe error suppression is more of like a term that is used within IBM, I would say. But errors correction and error mitigation, very specifically at the very least, are different. So error correction is something that is done to make sure that the qubits, right? The qubits are less noisy in some sense. You want to reduce the noise of, you want to reduce the errors coming out of errors coming at the qubit level. So you do something like use error correcting codes and the like. So that error correction sort of refers to that. Whereas error mitigation, it's more of a very often it is usually a sort of classical post processing or some kind of trick to reduce the noise while the processing is happening. And you don't necessarily have to do this at the qubit level, and it's often not done at the qubit level, right? So techniques such as twirl readout error extinction, where you do some measurement twirling, or zero noise extrapolation are examples of this. So the downside of using error mitigation is, in some sense, you have an extra computational overhead over like what you're already doing. But the good thing is that you observe more efficient results, or you get more accurate. You slightly reduce the effects of noise, and you get slightly more better fidelity in terms of your results. So, okay, what are some, so there's another term, there is another topic related to these sampler and estimator primitives that we can discuss, which is execution mode. So, to optimally run workloads on your system, there are 3 different execution modes which now exist. One is job, the other is batch, and the third would be sessions. So what is a job? If you're just running a single job, then you would say, in this case, in the case when you're initiating the sampler, right? Yeah, or the estimator in this case, you just, here it says backend, right? This is essentially mode equal to backend. So mode equal to backend means this is the execution mode we are talking about. Here you're just running a single job. But say, for example, that you have multiple jobs you want to run, and you would like it to have like be executed fast, right? So then you would run it as a batch. A batch specifically is good for non-iterative workloads that can run concurrently in machines and be parallelized. So you can then otherwise specify mode equal to batch. But if you have iterative workloads, for example, which is most often the case in the in like for variational quantum algorithms, then you would say mode equal to session. And the advantage of using a session is that when you use a session, no other jobs like would be run like that. When you initiate a session, the QPU time is exclusively reserved for you, so that one job finishes running, the classical compilation will be done, and then next, after that, following that, you will have another job running. And you won't have any jobs there won't be any changes in calibrations either, so during this time, so you can make sure that you eliminate any errors that can come from that side as well. So benefits of batch mode versus a single job with multiple circuits is that you have better concurrency of classical processing, and you can get individual results sooner. So this is if you have if you initiate a batch, this is potentially what the job flow can look like. And the way to implement a batch, so the batch implementation of the batch has slightly changed. Okay, sorry. It has changed a little bit in the sense I wouldn't say it has changed, but depending on the Qiskit version you use, right? It can be either backend equal to backend or mode equal to backend. So that is something you will have to learn to look at the documentation for. And as a just side remark, I would say that, yeah, like Qiskit, there are changes that come up frequently in Qiskit, but these are to help some improvements and add new features that didn't exist before, right? As hardware advancements are happening, the software stack has to keep up. It has to give speed, quality and scale. Otherwise, if these are not reflected on the software as well, you cannot um, harness those advancements which are coming in the hardware through the software as well, in turn your program, right? So I would say one of the best practices in general of anyone who's using quantum computing, not just for like this, not just for Qiskit, but for any SDK, is to often refer to the documentation, because most often whatever changes are there would at least be reflected in one place, which is the documentation. And knowing how to like look at the correct documentation is also important. Follow official sources, look at what is the latest version of Qiskit or other SDK that is out, and make sure that you're referring from the latest version, or at least the latest stable version where things are working well. So if this is a practice which you can inculcate, it's going to be like relatively easier to adapt to the to fast changes in different SDKs that you can see. So yeah, that is like about how you can start a batch, um, how you can run your primitive in a batch mode, versus if you have a session that allows iterative workloads. So you will have an estimated job, then you will have some idle time on your QPU while classical post processing is going on, then you will have the second job and you have idle time, and so on. But if you know how to kind of there are certain tricks you can use to kind of even use up this idle time, but that's more of an advanced technique. But it is possible. However, like in sessions you mostly have iterative workloads because you don't have any changes in calibrations, the noise profile is going to be uniform, etc. If you are going to run a variational quantum algorithm, then this is usually a good place to this is a good mode to execute your primitive in. So the last step of the Qiskit pattern would be post-processing results. So you have something called as a Qiskit visualization, which you can use to kind of plot histograms, get some coupling maps from that you can get from other places also. But you will find various tools in Qiskit visualization to visualize your results. So plot histogram is something that's very commonly used to get the counts result from sampler. Then you have post-processing techniques like circuit knitting as well, where during the optimization step for optimizing for hardware step, you decompose the problem into smaller circuits by using circuit cutting. And you execute these smaller circuits and then you knit these results back together to get the original circuit's outcome. So yeah, that's where I will kind of finish the lecture. So before we stop, like a short recap and summary, we looked at what is the anatomy of a quantum computing service. Basically, how do you go from a quantum algorithm that you've constructed to implementing on the quantum hardware and getting the results. You basically write your quantum algorithm as a quantum program using some quantum SDK. Then you then you connect to the some cloud service, say for example via Qiskit runtime service, and then your job will go to some laboratory, and then from there it will go to the control electronics, then it will get converted into pulse sequences, go to the hardware, get executed on the hardware, the results will come back, and then it just goes back the same way it came from until it reaches the Qiskit runtime service. It gives the results back, and then you again reinterpret those results using your quantum, using the Qiskit SDK or the quantum SDK that you used. Then what is a quantum SDK? It's a framework that has tools and allows you to convert your quantum algorithm, which you may have written on paper, into a quantum program that is compatible with other services that will let you run things on a quantum hardware. Then we looked a little bit into what is Qiskit SDK. We discussed the Qiskit ecosystem. We looked at how you can do some implement some basic things with Qiskit. This I'm sure has been covered by other lectures as well, that's why I didn't spend too much time on it. Then we looked at Qiskit patterns. Basically, how do you take a practical problem, map it onto a quantum computer, and actually solve it using the quantum computer. So in under Qiskit patterns, you basically have to convert your you have to embed your problem into the qubits and manipulate the qubits, which is essentially the quantum state. You basically evolve the quantum state using some quantum circuit, which is designed based on the algorithm that is going to solve your problem. So then once you have the circuit, you have to transpile the circuit and do some other software, and then make some manipulations based on software dependent architectural requirements for running on hardware. For example, you have to make sure that the transpiled circuit which comes is an ISA circuit, and then like you have to give the input to the sampler in terms of a sampler pub, or an estimator in terms of an estimator pub. So these are some of the steps that you have to take care of. And then you actually execute those circuit, like those you actually execute a primitive, and then once you get the results back, you have to post process these results. And after that, you also have techniques to get good results in the presence of noise. Yeah, which are basically some error mitigation techniques. I didn't discuss them in much detail, but just to make sure that I just wanted to touch upon those to say that these techniques exist. So thank you. We are coming to an end to this session. Any questions? I think there are quite a few.
Yes, ma'am. Thank you so much. And please take the questions one by one.
Sure.
And maybe somewhere in between, you had also mentioned that I'd like to show the this thing also, simulation, if there's any.
Yeah, I do have it, but there may not be enough time to like see that, and I'll also answer the questions. So should I
First
just
we'll
show?
take the questions. Yeah, first we'll take the questions.
Okay. Okay. Okay, so question is, are there any tensor network methods incorporated in Qiskit for handling exponentially large Hilbert space? Can you give a brief overview of it? So, okay, tensor network methods are usually more along the lines of simulations. So you can do like tensor network based simulations on using Qiskit if you want to build that. But like Qiskit is an SDK which is being developed so that you can handle exponentially large okay, I wouldn't still say exponentially large, but large Hilbert spaces on a real quantum computer. So Qiskit can, in that sense, Qiskit can handle large Hilbert spaces, but through tensor network methods, I wouldn't really say so. Like because it's more of a from what I understand, it's more of a simulation related technique. So yeah. What does the Qiskit SDK offer to developer, and what are the benefits of using Qiskit runtime over traditional execution? Qiskit SDK helps you kind of write your program, like your quantum algorithm in terms of a quantum program. It is one of the most widely used quantum SDKs. It's also open source. And what are the benefits of Qiskit runtime? If you want to use quantum hardware from IBM, you have to connect to Qiskit runtime. So there is that. I don't quite understand what you mean by traditional execution here. If it's more along the lines of using a simulator, the answer is that if you want to use a simulator, you can use Qiskit Air or your local simulator from even, I think Qiskit has a native simulator, so you can use whatever you want. Actually, now it has been moved to Qiskit Air. So for doing the simulation, you have to use Qiskit Air. But if you want to use a quantum computer, you have to connect to Qiskit runtime. Can you utilize Qiskit for matrix operations? You can use Qiskit for, so you can use, so for doing for operator related, for using operators and the like, you have to import things from qiskit.quantuminfo. So if you look at qiskit.quantuminfo, you can look at where all the operator mechanics related stuff is in Qiskit. So you can explore that documentation to see what you want to do. Is it going hands-on? It should have, but let's see if we have enough time. Can you please give us some details about how we can validate protein structure prediction using quantum? Okay, to be very frank, right now it's the stage where it is at is you validate quantum structure, protein structure prediction results from quantum using classical. But hopefully in the future, like once we are at utility and we are able to solve good practical stage problems, quantum can become the standard. But I mean, like this question, I'm not sure if I'm interpreting it correctly. If you mean how can we do protein structure prediction using quantum, um, I just gave a brief explanation of that before during the lecture itself. But it's a question which will by itself be a lecture. So I would say that, okay, to answer that question in a couple of lines, you basically encode the geometric information of a protein, basically the structural information of the protein into the qubits. Then you can use a variational quantum algorithm such as VQE to prepare a quantum circuit, or specifically a parameterized quantum circuit. Then you find the cost function. Then you define the cost function around the energy of the protein, basically taking the expectation value by constructing a Hamiltonian, and you minimize that energy, and whatever parameters you get out of that, that will give you the answer for the structure. What would be the predicted structure of the protein? Sorry if it was a bit like it was, I know it may not be explain everything, but that is the shortest answer I can give to that question. We can use unitary operator in such case. I'm not sure about in which case you're mentioning, but all of quantum computing, like to create a quantum state or to evolve a quantum state, whatever, we are using unitary operators everywhere. So the answer is probably yes. So is estimator devoid of measurement? Yes, in some sense, the estimator is devoid of making individual measurements. But if you make individual measurements, you can still, estimate expectation values. Yes, there is. Okay, we need to allow backward compatibility as we usually do for any tool development. Yes, from Qiskit, the reason Qiskit 1.0 release was very important was because from then on, you had backward compatibility. So this is sort of being taken care of. Any practical problem solved by Qiskit? I mean, I wouldn't say Qiskit specifically, but any practical problem for quantum computing is being solved. Yes, we are kind of trying to do that only. There were some breakthroughs in terms of utility scale workloads and the like. So yes, it's ongoing research, but everything looks promising. Please explain the last slide once again. I'm not sure which one you're talking about. Decomposition. Okay, I'm not sure which question this is, so I'll just go to the next question. What research paper level experiments can be feasibly executed within the free access limits of these simulators and quantum IDEs? Okay, so this is, if you want to get to a research paper level experiment, it may not be very easy to do all of it in a free access limit. Okay, but simulator you can definitely do, because there is no, like, simulator is something that you can run on your computer itself, like especially like whatever is there in Qiskit Air, you can use simulators up to a good number. But what research paper level experiments, there are some I can think of, but it really differs from, like, depends on what kind of problem you want to work on. So for smaller, but you will have to restrict yourself to smaller number of qubits in order to be able to make sure that you are within the limit of usage, if you are even thinking about, say, quantum computers. If there is an error coming at a particular step, how do we come to know if the error occurred at quantum hardware? Do we get some response from quantum service runtime? Meant if correct expectation reporting is in place. Okay. So I think you are more about asking about whether we can understand the noise profile in a quantum circuit in a better way. Yes, there are many ways to understand what the noise. Okay, so the noise can come from individual qubits. It can also come when you implement specific gates. So like first of all, if you want to understand how much readout errors and all are there on individual qubits, that you can do by looking at the compute resources section of the like hardware. For example, sorry, yeah, if you for example click on say for example IBM Sherbrooke. If you hover over, okay, I don't think that is working. Usually you can see the error, readout assignment error. Yeah, here it is visible. So you can see the readout or assignment error on various qubits, and you can also download this data. This will change based on the calibration. So here you say it says last calibrated how long ago. So this will change on this will change a bit based on the most recent calibration, but you can access this data, like how much error or how much readout error is there on individual qubits. Similarly, you can also look at the like you can also understand the 2 qubit error rate in like various qubits, but that basically means, yeah, see, now you can see this basically means that if you implement an ECR gate between 115 and 116 qubits, this is the ECR error you can expect. So you can see this graph representation of this as well over here. So that is one way for understanding the errors on individual qubit level. Aside from this, there are also techniques such as polytwirling, which you can apply. There is something called as a noise learner. So for example, like if you do polytwirling, which is usually included with error mitigation techniques, but it is more of a noise tailoring technique. What you do is you take, so essentially in your quantum hardware, the noise is very unpredictable, right? You don't know where there could be multiple sources of error in the same qubit or the same or the gate. There could be some crosstalk errors, etc. So you don't know where exactly the error is coming from. However, you can like take this random noise and you can convert it into a more predictable sort of noise by doing polytwirling. Essentially what polytwirling does is it converts randomized noise in your circuit into stochastic noise. Why stochastic noise? By basically you convert whatever noise is there in terms of some polys into a poly noise channel. So these by polys I mean poly gates. So they may not be the same every single time. However, it still gives more structure to your noise. So once you know what the structure is, you can mitigate that noise. And noise learner, again, it helps you learn the noise of different layers in your circuit. What do we mean by layers? When you have, say, circuit depth 10, right? You can say the first layer is the depth 1, second layer is depth 2, depth 3, and so on. So those are layers. You can learn the noise of corresponding to specific layers using the noise learner. So that's again something that you can explore in the Qiskit documentation. Any info on scalability issues in programming? I am not quite sure what this question means. So I think I have to skip this one. What is OpenQASM3 and what is Qiskit? So Qiskit so Qiskit is it's a higher level programming language where you can talk about operators and, like you can talk about building circuits in specific ways or doing like manipulations on a higher level. OpenQASM3 is a more of an intermediate representation or assembly language. So what happens is once you submit a program to Qiskit, eventually it kind of gets converted to QASM3. So if you have to manually write everything from scratch using QASM3, it's not very easy. However, if you write using Qiskit and then like you transpile and you actually implement it on some hardware, that time it will automatically be converted to OpenQASM3 because it's an intermediate representation. Qiskit SDK is going to be updated by IBM in July. Will it be a massive change compared to what we've learned today? So Qiskit SDK undergoes regular updates, right? Right now we have, we recently came out with 2.0 and sometime later, I think 2.1 is also out. So there will be releases 2.2, 2.3 and so on. But as I mentioned, it will usually be to add new features or improve some existing features. So learning that is going to be of benefit for you if you want to implement things on hardware. Is it possible to implement communication techniques in Qiskit simulation? I assume you mean quantum communication protocols. Yes, it is possible. It is definitely possible to do so in Qiskit. I mean, uh, I'm saying that it is possible very loosely, but it depends on what you are trying to do, right? If you want to implement, say, for example, something like a basic teleportation circuit, you can do that. But can you do practical stuff there? I don't really think so. But to understand or do some theoretical studies, it may be possible. Okay, also I was participating. I am not aware of this, like the part where, I don't quite understand the question exactly. I think the way it is being posed. So I'm going to be skipping that. Can security problems be solved by using Qiskit? I assume you may mean, can you do some kind of quantum cryptography using Qiskit? Of course, you can do like quantum cryptography based studies using Qiskit, but I don't if you want to solve some kind of cyber security issues, I think that's a different question. Can you share some Qiskit simulation code? You can already find some basic code. I think others might have also discussed it. I don't think we have enough time to go through the hands-on session today, but there are many, like you can find this even online. I'll try to share something though. Okay, while running job on real device through IBM Composer, it shows job failed message. I can't identify the error. Okay, actually here there was some, somebody reported, so there was some issue here, but I think it will be fixed by next week. You please try again next week. I think it should be fixed. There was some bug with OpenChasm. So that kind of came through to Qiskit as well. So there was some issue with the OpenChasm part when it was compiled to Qisk, after, okay, there was a bug, there was sort of a bug related to the OpenChasm representation, but that has been fixed to my knowledge, because I did come across this error. So it should hopefully be fixed by next week. I think I already answered that question. For a gate that does not exist. Yes, you can. Yeah, you can do this. You basically, once you do, yeah, you can, there is a way to do this. For a gate that doesn't exist or does exist, can you use so the operator is operator is not a primitive, but then I assume you can represent a matrix as a, you can get a unitary operator sort of representation of matrix. It is possible. You will have to represent it in terms of a sparse poly, but it is possible. You don't, okay, do you have to study OpenChasm 3 also? It's not compulsory, but knowing it exists and learning how to interpret certain things in that will help you understand how things work when they are being implemented on hardware level. When would you typically use OpenChasm? So you don't, if you're trying to use, implement some kind of a quantum algorithm, you don't have to, write things directly in OpenChasm. But you can, you can use it to come up with you can write programs in it, but it's not really necessary, because quantum SDKs will do that for you anyway. Okay. Difference between passing backend to estimator and batch backend equal to backend. Okay, so this is you saying batch of backend equal to backend is the way to initiate a batch, right? Like you initiate a batch. Yeah.
The questions that you got personally, can you please read it out? Because it's not available on the chat here, right?
Right.
So read the question and then answer. Otherwise, the context is not understood. Yeah, thank you.
Sure. Sorry. Okay, the previous question was when would you typically use OpenChasm? This was a very simple question, but I think it was implied, but that was the question. The next one, which has come privately, is what is the difference between passing backend to estimator of backend and batch of backend equal to backend? Let me go back to that slide actually. Um, Yeah, here this is just a way you are starting a batch. You are initiating a batch here. And then, like usually you would also say sampler of mode equal to backend as well. So this is to make sure that so saying, estimator of backend is to tell that to tell the estimator object that you are actually running it in a like backend mode. Okay, these are two different things. So estimator of backend is specifying a mode for the estimator. So if you're using estimator in a batch mode, you would say estimator of mode equal to batch. Saying batch of backend equal to backend or session of backend equal to backend is a way to initiate a batch or a session. So last question, can ML or DL models be enhanced using Qiskit? This is a very general question, but yes, there is a possibility of doing QML or quantum machine learning or quantum deep learning. It is very much possible. If very generally speaking, with quantum, how do you mix quantum ML and quantum? How do you mix quantum with traditional machine learning? There are actually three ways you can do it. So if you look at data encoding versus processing, you can have classical data encoding and classical processing, or you can have quantum data encoding and classical processing. You can also have classical encoding and quantum data processing, and finally you can have quantum data encoding and quantum processing. So among these four options, obviously options 2, 3 and 4 are a way to combine quantum with machine learning or deep learning routines. But again, that's a question that would take an entire lecture by itself to answer. So yeah, I think there are one more questions. Okay, ma'am, could you please share the codes in which you connect to the cloud file and all? I don't understand what you mean by cloud file. Okay, you mean the initiating the Qiskit runtime service. You can actually find that in the documentation of Qiskit runtime. So that's something available online. You just have to see how to connect to Qiskit runtime service. If you look that up, you should be able to find the documentation for that. Would we get sophisticated to the point of representing all classical gates in a quantum circuit to solve all levels of problems? In the sense, QCs become the new default hardware that everyone uses. This is a good question, but to answer this very honestly, even if we get to a point where you can represent all classical gates in terms of a quantum circuit, I don't think that quantum computers will become the new norm anytime soon, and they will completely replace all the classical existing hardware. Because as I mentioned sometime before, to do 3 into 5, you're not going to pull up, you're not going to write a sophisticated Python program and run it on a supercomputer. That's something you can just at most do mental math or just use a calculator to do it. So quantum computers are very useful resources, so you want to use them to solve problems of that level of practical difficulty. And not to mention, classical computers have been undergoing so much development across such a long time. Quantum computers are like more of a new technology. What I think will be more of the case is that in some time we already have CPUs, we have GPUs, even TPUs have come up, like tensor processing units have come up. QPUs will be an additional option for you to QPUs, basically meaning quantum processing unit. They will be an additional framework which you can use to run some part of your programs to do things that you cannot usually do with a classical computer or a, say, even a GPU or a supercomputer, right? So like the new idea of what we are looking to in terms of quantum advantage is we are hoping to realize that through the means of something we call quantum centric supercomputing, basically where you're using a quantum computer to do what it can do efficiently, in addition to some GPUs which can, say, for example, do some very efficient classical post processing. And what we hope to achieve by doing this is to either get some results with more accuracy than we have never been able to before, or to be able to do some things faster. So that's how we have right now redefined the notion of quantum advantage as well. So to conclude, QPUs will definitely become a huge thing in the future, but I don't think it is going to replace classical computers everywhere anytime soon. Yeah, that's my answer to the question. I think I've answered everything, and we are also 3 minutes over the allotted time. Thank you everyone for your attention.
Yeah, thank you so much, ma'am. Thank you for the wonderful session. And actually, we wanted you to give a break of 2 minutes in between.
So
but we
sorry
could not
about
stop
that.
you. Actually, what was the issue was we usually make a 1 hour videos, so that was the idea. But anyway, that's not a major issue. We can manage it. So, but then, yeah, continuously, I mean, I think you've been speaking. You have not given a pause also. So that was excellent. Thank you so much for very quick overview, I think. But yeah, let's see if we can actually have some time where you will be able to demonstrate some codes sometime. I'll get back to you on that. We'll see when it fits. There's one slot that's still available. I'll just see if you can come back, because yesterday we were hoping you will come, but of course we had a wonderful session from Dr. Jay Kumar, who took your session, I think, and that was great. So thank you so much, ma'am, and participants, we will join tomorrow. One announcement for all of you: the quiz exam, which was supposed to start today at 4 o'clock, will start tomorrow at 4 o'clock, right? So, and then it will proceed. We will keep it open till Sunday. Another request has come for quiz 1 also. Some people who have not written it for the first time, so we will open it again on Saturday. And if there are any problems, people have started attending the quiz and there was some issue, they have scored very less, or they got some disconnected or something like that, please let us know. Please message me or Radha Krishna or Dr. Vikas, and we will try to help you. And thank you so much for being with us. And thank you, ma'am. Thank you, Dr. Jay Kumar. Thank you, Dr. Anand Raman, and being with us. Vikas, any concluding words? Yeah, I think. Yeah, okay, Vikas. Yeah, thank you, ma'am. Ma'am, you're able to see your response from all participants who are thanking you for the session. Thank you. Thank you so much. That's a very good immediate feedback that you're receiving. Yeah.
Thank you.
Yes. Actually, the way PPT was explained was very much interesting. From the beginning itself, I was even interested in understanding all those things. The
Yeah.
PPT was well prepared actually and well explained. Thank you, ma'am. Thank you for your session.
Thank you, everyone.
Thank you all. We'll meet tomorrow at 2 o'clock, and 4 o'clock onwards will be your exam. All the best.
All the
Thank
best
you,
to
ma'am,
everyone.
once again. Yeah.
Thank you, everyone, for your attention.